Okay, let's look at number 72. So we have a rocket is rising vertically, right? So it's going up at 880 feet per second when it's 4,000 feet up. And so if I were trying to picture this as a video, what I should notice here is that this length is going to stay 3,000, but maybe sometime later it's going the height x, so x is going to be bigger, and of course this angle phi is going to also be bigger, right? So right, this is constant, and our two variables are the height of the triangle and the angle here. So, and I know those are not the straightest lines, but so what high school fact are we using here? We have an angle and we have a ratio of two sides, the opposite side and the adjacent side. So if you are saying to yourself tangent, then very good, you're right. The tangent of that angle is the opposite over the adjacent. So you do need to brush up on your SOHCAHTOA ratios in case that's not something that you remember from high school. Okay, because in this case it happened to be the opposite in the adjacent side, but it could very well be the hypotenuse or one of the other ones. So make sure you know your ratios. Okay, so this is the relationship that compares or gives the relationship between my two variables. And so the next step is to differentiate this with respect to time. So what is the derivative of tangent of some angle? Well, it's going to be secant squared of that angle times the derivative of that angle with respect to time, right? So that's our chain rule. And keep in mind that in this very instant, once I took the derivative, I am in radian mode because all of our rules of like the fact that derivative of sine is equal to cosine, that is all based on being in radians. Over here on the right side of the equation, as I've emphasized a few times in homeworks for you, I would not think of this as a quotient. I really want you to think of this as just 1/3000th as the coefficient x, right? Because now when we go to take the derivative, then I could just leave that 1/3000th coefficient alone and then times the derivative of x with respect to t. Okay, so now I've differentiated. Now I need to substitute in all the values that I know. So I do know that the rocket is rising at a rate of 880 feet per second. So that's telling me how fast x is changing, and it is increasing, so it's positive, right? So I know over on this right side, I know dx dt is 880. What else do I know? Well, I know that we're asking about how fast the camera angle must be changing, so I know that's going to stay a variable, d phi dt. But I still have to figure out what secant squared of phi is. So they didn't tell me what phi is, but I know that at the instant when x is 4,000, I could just compute that, right? So I have that, so when x equals 4,000, that's 40,000, sorry, 4,000, tangent of phi is going to equal 4,000 over 3,000. And so in radian mode, of course, make sure you're in radian mode, I'm taking the inverse tangent of 4/3 or 4,000 over 3,000, right? And so in radian mode, I'm going to get an answer like 0.9273. Okay, so I want to use that answer to find what secant of theta is and square it. So I'm going to keep this answer stored into my calculator and then take cosine of that answer. Okay, try not to round if you can. So take cosine of that answer, and your calculator will then know the exact value is 0.6 or 3/5. So if cosine of the angle is 3/5, then secant of that angle must be the reciprocal. So that's got to be 5/3. And so then, let me scroll down just a notch here. Scroll down. Sorry. I was right-clicking accidentally. Oh, okay. I'm going to run out of space anyway. Where do I want to put this? So we'll just put over here. So secant squared of the 0.9273 would be 25 over 9. Okay, so all of this is 25/9. So now doing some algebra to solve for d phi dt, I'm going to multiply both sides of the equation by 9 over 25. And so that'll simplify to 66 over 625, or if you're a decimal person, 0.1056. And what are the units here? Well, we're talking about how fast this angle is changing, and the angle is in radians. and then the units of time is per second. So we're looking at approximately 0.1056 radians per second.